Have you ever just stopped and looked at your phone or your computer and wondered how on earth it actually works? I mean, what makes the materials inside these devices neither a conductor nor an insulator, but something entirely magical right in between? How do we actually control electricity, literally telling it exactly when to flow and when to stop dead in its tracks? It's a problem that seriously baffled early scientists, but as we'll see, semiconductor physics solves it just beautifully. So, welcome to this explainer. I am absolutely thrilled to take you on a journey into the incredibly precise world of atomic engineering. Today, we're going to demystify the magic middle ground of semiconductors, and we'll look closely at how manipulating just a handful of atoms has, well, completely revolutionized the modern world.
Here is our quick roadmap for today. We'll start by defining this magic middle ground. Then we'll zoom way in inside the crystal lattice. After that, we'll explore how to introduce useful imperfections, build a pn-junction diode, direct some electrical traffic, and finally, we'll test our real-world engineering limits.
Okay, let's dive right into Section 1, the magic middle ground, beyond conductors and insulators. Let's look at what fundamentally separates a semiconductor from, well, pretty much everything else we find in nature.
These numbers really tell the story. The extreme contrast in resistivity here is pretty revealing. Resistivity just tells us how strongly a material opposes the flow of electric current. Look at the top row. We have copper, a classic, fantastic conductor with a tiny resistivity of 1.7 times 10 to the negative 8th power ohm meters. Then down at the bottom, glass, a classic insulator, comes in at a massive 9 times 10 to the 11th power. But right in the middle sits germanium at 0.6 ohm meters. It's not a great conductor, but it's definitely not a great insulator either. This unique placement is exactly why elements like germanium and silicon are classified as semiconductors. They occupy this highly exploitable middle ground. Let's move on and see how this actually works when we look closely at the atoms themselves.
Moving right along to Section 2. Inside the crystal lattice, the atomic building blocks. To truly understand why germanium behaves this way, we have to zoom way in. We're going from the macro properties you could measure on a workbench all the way down to the microscopic atomic structure.
So, germanium and silicon are what we call tetravalent elements. All that means is they have exactly 4 valence electrons hanging out in their outermost orbit. Now, nature loves stability, right? An atom really wants 8 electrons in that outer shell to be perfectly happy. So what do? Each germanium atom positions itself to share 1 valence electron with 4 of its neighbors. This whole business of sharing sets up what are called covalent bonds. It creates a neat, incredibly orderly, and deeply interconnected crystalline structure. At absolute zero temperature, these bonds are tight. I mean, there are 0 free electrons, and the material actually acts like a perfect insulator.
But here's the thing, we don't live at absolute zero. When we introduce thermal energy, literally just regular room temperature, something totally fascinating happens. The heat supplies just enough energy to break some of these covalent bonds. If we think about it in terms of energy bands, the electrons bridge the forbidden energy gap, which is about 0.7 electron volts for silicon and 1.1 electron volts for germanium. Actually, wait, strike that, it's the other way around. 0.7 for germanium and 1.1 for silicon. And they jump straight from the valence band to the conduction band. And here's the real magic trick. When an electron breaks free, it leaves behind a vacancy in the bond, which we call a hole. This hole acts exactly like a virtual positive charge. It's kind of like an empty seat in a crowded theater. As people shift over to fill it, the empty seat appears to physically move across the room. Heat creates these whole electron pairs, giving us our very first taste of electrical conduction.
Which brings us to Section 3, doping, useful imperfections. Because while heat does create a little bit of current, a pure intrinsic semiconductor is still, frankly, pretty useless for electronics. There just aren't enough free electrons or holes. To make them useful, we have to intentionally break their perfect structure.
And this brilliantly illustrates how we do it, through a process called doping. We're basically adding incredibly small amounts of impurities, and we do this in 2 distinct ways. On one side, we add a pentavalent impurity like arsenic. Arsenic has 5 valence electrons. 4 of them lock into the crystal lattice perfectly, but that 5th electron has nowhere to go. It becomes a free electron. Because it provides extra negative charge carriers, we call this an N-type semiconductor. On the flip side, we can add a trivalent impurity like gallium, which only has 3 valence electrons. It bonds with 3 germanium neighbors, but it leaves a hole where the 4th should be. This abundance of positive holes creates what we call a p-type semiconductor.
This brings up a really vital concept, majority and minority carriers. In our N-type material, the extra electrons are the majority carriers, and the few holes created by room heat are the minority.
In p-type, holes are the majority and electrons are the minority. Now here is a wild fact that trips up almost everyone. You might think an n-type material has a net negative charge and a p-type has a net positive charge. Nope, they don't. The impurity atoms we added, like arsenic or gallium, are completely electrically neutral to begin with. Their protons perfectly match their electrons. So the absolute crucial takeaway here is that even though we've shifted how the material conducts, both n-type and p-type semiconductors remain perfectly electrically neutral overall. Pretty cool, right?
All right, section 4, the pn-junction diode, smashing materials together. So we have these two distinct, highly engineered materials, n-type and p-type. The real magic of modern electronics begins when we join them together to form a single crystal.
The very moment a p-type and n-type block are fused, this crazy microscopic event happens instantaneously. As the materials join, the dense crowd of free electrons in the n region naturally diffuses across the junction. It's like a microscopic stampede. As they cross over, they fall into the abundance of holes on the other side, completely canceling each other out. This ultimately leaves what we call a depletion region, a tiny, narrow border zone that is completely emptied of its free charge carriers.
As those electrons abandoned the n side, they left behind positive ions, and as they filled the holes on the p side, they created negative ions. These layers of positive and negative charges set up a localized electrostatic field. It essentially acts as an invisible wall, a barrier potential, that physically stops any more electrons from diffusing across. For silicon, this natural wall stands at about 0.7 volts, and for germanium, it's about 0.3 volts.
Moving on to section 5, directing forward and reverse traffic, the power of biasing. So we have this microscopic barrier. How do we actually control it? Well, we do it by applying an external voltage from a battery, which is a concept known in electronics as biasing.
Think of biasing like directing traffic. If we hook up the positive terminal of a battery to the p-type and the negative to the n-type, we are forward biasing the junction. This external force pushes against that internal barrier, shrinking it down and allowing current to freely flow. But if we flip the battery, connecting positive to n-type and negative to p-type, we create reverse biasing. This literally pulls charges away from the junction, expanding the barrier and blocking current completely. Boom! We have just created a one-way traffic valve for electricity.
Now what's really interesting is how this looks physically. In forward bias, the external field totally opposes the barrier potential, physically shrinking the depletion layer until it offers almost zero resistance. It's wide open. On the flip side, in reverse bias, the external field aligns with the barrier potential. The depletion region expands massively, establishing this huge, high-resistance path where practically zero current can get through, except for a tiny trickle from those minority carriers we talked about earlier.
Okay, section 6, VI characteristics and limits, real-world engineering. Let's transition from the abstract physics to some practical, real-world engineering. How does this PN junction, which we also call a semiconductor diode, actually perform when we hook it up to instruments in a real circuit?
When we map this out, we get the volt-ampere, or VI, characteristic curve. It is the definitive map of how a diode behaves. When external voltage is 0, current is exactly 0. As we start applying forward voltage, pushing right on the graph, you'll notice the current barely creeps up at first. That's because the external battery is spending all its energy just fighting that internal barrier potential. But once it overpowers that barrier, whoosh, the current skyrockets upwards in an almost straight line. The diode becomes a fantastic conductor.
That magical turning point on the forward curve sits at exactly 0.7 volts for silicon and 0.3 volts for germanium. It's called the knee voltage. But look what happens if we apply reverse bias, pushing backwards on the graph. The current is virtually flat, effectively 0. However, if you push reverse voltage way too far, you hit what's known as the breakdown voltage. The minority carriers acquire so much kinetic energy they physically smash into atoms, knocking loose more electrons, creating this crazy destructive avalanche of free electrons. The current suddenly spikes downward, and you've permanently destroyed the junction.
Which naturally brings us to our practical engineering limits, because you can't just push infinite power through a diode unless, you enjoy the smell of burning silicone. Manufacturers actually give us 3 strict rules. First, maximum forward current, that's the highest current it can handle before excessive heat simply melts the junction. Second, peak inverse voltage, or PIV, the absolute maximum reverse voltage you can apply before you trigger that destructive avalanche breakdown we just looked at. And third, maximum power rating, just the total heat dissipation the package can safely handle. Exceed any of these, and your delicate, beautiful atomic-level engineering melts back into a useless lump of material.
So we've seen how doping germanium and silicon allows us to build a tiny, solid-state one-way valve for electricity, the pn-junction diode. But I want to leave you with this final, kind of mind-blowing thought. If joining just 2 doped layers gives us this much incredible control, what world-changing, revolutionary device might we create if we sandwich 3 layers together? Well, the answer to that question is the transistor, and it's literally what makes the entire digital age possible. Thank you so much for hanging out with me in this explainer. Keep wondering, keep learning, and I'll catch you next time.